Welcome, class. This is our third lecture on fundamental concepts in chemical engineering, wherein today we'll be reviewing the critical underlying physics of chemical engineering. By the end of this class, we aim for you to have grasped these fundamental physical concepts, including those on Newton's laws of motion, mechanical work, power, and efficiency, energy conservation principles in mechanical systems, rotational motion concepts, and angular momentum conservation in rotational systems. Before we get too deep into equations and forces, I want to pause and highlight something very basic but absolutely essential, and that is units. In science and engineering, we use what's called SI units, the International System of Units. And you'll see them everywhere in chemical engineering as well as beyond, in science more generally. These are the standard measurement units we use to describe physical quantities. So for example, mass is measured in kilograms, length in meters, time in seconds, and force in newtons, which is also the same as kilograms by meters over seconds squared, and so on. It'll be important for you to remember this, as well as that joules is newtons by meter, and that watts is joules per second. Knowing your SI units is, however, more than just memorizing the different units of measure. It's also a powerful tool for catching mistakes. For example, checking if your equation makes sense, and helping you reason through unfamiliar problems. Take here, for example, Newton's second law, which we will cover a bit later in this lecture also. It is force equals mass times acceleration. So let's do a dimensional check on this. Mass has units of kilograms. Acceleration is in meters over seconds squared. So if we multiply these two together, we get kilograms by meters divided by seconds squared. And this is indeed a Newton. So this matches up with the definition, and thus we know this equation is dimensionally correct. If units don't match up, it's likely a big red flag that something in your equation or calculations has gone wrong and is worth revisiting or rechecking. While we've discussed SI units, you might still run into imperial units, especially in US industry, like horsepower, which is commonly used instead of watts. So I've included a key of conversions here. We won't go deep into the imperial conversions in this lecture, but it's important for you to know that they exist, and engineers often have to convert between them. Let's start with Newton's first law, also called the law of inertia. This law tells us what happens when there's no net force acting upon an object. If the object is at rest, it stays at rest. If it's moving, it keeps moving at the same speed and direction at a constant velocity, unless something acts upon it, like a push or some friction. Think of a hockey puck on ice. Friction is very low on ice, so it glides in a straight line until it hits something. Mathematically, we can write this as such. This equation says that if the net force is zero, there is no acceleration, and that the velocity remains constant. That includes the case where velocity is zero, so the object could be sitting still. We can check this idea using equilibrium conditions. We say an object is in equilibrium when forces cancel out in all directions. Let's look at a simple example, something just sitting on a table. There are two vertical forces, gravity pulling down, Fg, while there's also the table pushing back up, which is the normal force, Fn. When these two are equal, there is no vertical motion. So to summarize, Newton's first law is about what happens when no net force. Things don't start or stop moving on their own. Forces are needed to change motion, not to keep something moving. And if all forces cancel out, the object stays exactly as it is. Now we move on to Newton's second law of motion, the law of acceleration, and it's one which really drives most of our engineering problem solving. In maths terms, this is the net force equals the mass times acceleration. The net force is the total forces acting on the object. Note here also that there is an arrow above both force and acceleration. This indicates that they are vectors and thus direction matters. M is the mass, which tells us how much the objects resist acceleration, whereas A, the acceleration, is how fast the velocity is changing. So more force means there's more acceleration, unless you have a lot of mass resisting it. We often work with forces in different directions, especially in 2D motion. So we can split the vector equation into different components. This helps us solve for horizontal and vertical motion separately and apply our problems. Let's now look at the derivation of Newton's second law, which can actually be derived from the definition of momentum, denoted as P, which is equal to the mass times velocity. If we take the rate of change of momentum, we get this equation which says that the F vector equals the time derivative of momentum vector. That is, force is equal to the change of momentum over time. And if the mass is constant, which is typically the case for a solid object, this then becomes force equals mass times acceleration. So Newton's second law is really just saying that force is what causes momentum to change. This law is thus at the heart of all mechanical analysis, and if something is accelerating, this law tells us what's causing it. Let's now apply what we just learned about Newton's laws to a very simple case. What forces act on an object that's just sitting still? Let's say we have an object or a piece of equipment that weighs 100 kilograms, and it's resting flat on the ground. The first and most obvious force is gravity. Gravity pulls the object down toward the center of Earth. We call this force the gravitational force, or Fg, and we calculate it using Fg equals the mass times gravity, where mass is the mass in kilograms and g is the acceleration due to gravity, which is 9.8 meters per second squared. So for this block, the gravitational force F is equal to 100 times by 9.8, which is equal to 980 newtons. Remember that Newton is derived unit equal to a kilogram meters per second squared. So the units here check out. Now, if there was no upward force to balance that downward pull, the object would fall through the floor, but it doesn't, which means that there must be an equal and opposite force pushing upwards. As we have learned, this is called the normal force. So at rest, the normal force equals the gravitational force. And in this case, that is 980 newtons, as we've just calculated. As these forces are equal in magnitude but opposite in direction, they also cancel out. That's Newton's first law in action. And if the object is at rest, the forces are balanced. Thus, we can say that the object is in vertical equilibrium. Now let's apply Newton's laws to fluids, specifically particles floating or sinking. Here's the key question. Do particles float or do they sink in a fluid? To figure that out, we look into two main forces acting upon a particle. The first is gravity, pulling it down, with the equation of the gravitational force being equal to mass times gravity. The second force is the buoyant force, pushing upward. The buoyant force is equal to the density of the fluid multiplied by the volume multiplied by gravity. Now, the mass of the object or particle isn't always given directly, but we know it's related to density and volume, where mass is equal to the density times by the volume. So we can substitute that into our gravity equation, making this a kind of a battle of densities, the object's densities versus the fluid's densities. But as you can imagine in this image, the object is sitting in the fluid, and you have gravity pulling down and buoyancy pushing up. We're asking which one wins. If the object is just floating, not moving up or down, that means the forces are balanced. When that happens, the density of the particle equals the density of the fluid, and the particle floats in neutral equilibrium. Now, if the object or particle is more dense than the fluid, it will sink. If it's less dense, it will float. So you don't always need the full force equation. Sometimes just comparing densities is enough to know what will happen. This idea shows up in many chemical engineering processes, from sedimentation in wastewater to flotation in mineral recovery and fluidized beds in reactors. We don't go too deep in this lecture course, but just to know, Archimedes' principle underpins a lot of separation and mixing technologies. Let's look at how Newton's second law applies when we try to move an object along a surface, like sliding a heavy piece of equipment. If we apply a force F from the left to try and move a box, but something's pushing back, this is likely friction. Newton's second law tells us that the net force on the object causes it to accelerate. So the net force is equal to mass times acceleration. So if we want the box to accelerate, there has to be a net force, not just an equal or opposite one. But we don't get to apply force in a vacuum. Friction is always pushing back. So the net force is what's left over after friction. The net force is equal to the force applied minus the friction force. This is why sometimes it feels hard to push something, even if you're applying a lot of force. Friction eats up much of that energy. Friction depends on how grippy the surface is. We calculate this using these formulas. Firstly, static friction. So this resists starting motion and is equal to the static coefficient multiplied by the normal force. So Fs is equal to static coefficient multiplied by Fn. And the kinetic friction, so once it's sliding, is equal to the kinetic friction coefficient multiplied by the normal force, where these frictions are unitless and have characteristic value for a specific material. Let's compare two different surfaces, ice and carpet. Ice has a very low friction coefficient. It takes very little force to slide something along it, whereas carpet has a high friction coefficient. It resists motion much more, so we need to apply more force to get the same displacement. This is why you can slide on an ice rink, but not so easily on a road. So Newton's second law still holds, but in the real world, we almost always have to subtract friction to find the net force. Less friction means more of your applied force goes into accelerating the object. And remember, no acceleration happens unless the net force is non-zero. Let's work through this example using Newton's second law in friction. We have the same 100-kilogram piece of equipment sitting on a concrete floor. There are two parts. First, we'll find the minimum horizontal force needed to start the object moving. Then we'll find the acceleration if somebody pushes it harder than this minimum horizontal force. To move the object, we have to overcome static friction. Static friction resists motion until we reach a certain threshold, and then the object will start to slide. We first calculate the normal force, which is, in this case is just the weight of the object multiplied by gravity. As we previously shown, is 100 multiplied by 9.81 equaling 980 newtons. This is the force the surface is pushing upward on the object, and it's what the static friction depends upon. Now we use the static friction formula, where static friction is equal to the static friction coefficient multiplied by the normal force. Substituting in the values, we get 0.6 multiplied by 980, which equals 588.6 newtons. That means that we need to apply at least this amount of force to get the object moving. In part B, we're told that a horizontal force of 700 newtons is being applied to the equipment. We want to know what is the acceleration of the equipment once it's already started moving, assuming the coefficient of kinetic friction is 0.45. We go straight to Newton's second law, which says that the net force, which causes acceleration, is what's left over after subtracting the force of friction from the force applied. Now let's calculate the kinetic friction force using the kinetic friction coefficient multiplied by the normal force. Here the normal force is still 980 newtons, and we are given the kinetic friction coefficient, 0.45. Thus the friction force is 0.45 multiplied by 980 newtons, totaling 441 newtons. This is the amount of force the floor is using to resist motion. Now let's plug this into the net force formula and solve for acceleration. So we get 100 kilograms multiplied by acceleration is equal to 700 newtons minus 441 newtons. Rearranging, we can solve this, and what we find is that acceleration is equal to 2.59 meters per second squared. Now that the object is in motion, static friction is no longer involved. We subtract kinetic friction instead, and use the remaining net force to find acceleration. This is a classic Newton's second law application, i.e., you calculate net force, then divide by the mass to get acceleration. Let's now take it one step further. We know the object is accelerating at a rate of 2.59 meters per second squared. What if we want to know how far will the box move in 10 seconds, starting at rest? To solve this, we will use the kinematic equation for constant acceleration, which is displacement d is equal to the initial velocity v0 times by time, plus 1/2 times acceleration times time. Now let's plug in our known values. That gives us 0 times by 10 for v0 times t, plus 1/2 times 2.5 multiplied by 10 squared. This gives us a displacement of 129.5 meters. So if the object continues accelerating at the same rate, it will travel 129.5 meters in 10 seconds. This is a great example of how we connect forces and motion. We use Newton's second law to find acceleration, and now we use kinematics to find how far the object moves in that acceleration over time. This bridges the gap between force-based physics and motion-based prediction, something we'll keep building upon. Newton's third law is often called the law of action and reaction. It famously says, for every action, there is an equal and opposite reaction. This means that forces always come in pairs, and they act on different objects. We write this as the force of A on B is equal to the negative force of B on A. This means if object A pushes on object B with a certain force, then object B pushes back on object A with a force of the same magnitude, but in the opposite direction. Let's take this example. A person is pushing on a 100-kilogram box. The person exerts a left to right force on the box, but at the same time, the box is pushing back on the person with an equal right to left force. That's why when you push something heavy, you feel it push back. It's not imaginary. It's the reaction force acting upon you. As another example, we can think of, for example, a motor mounted something. As it applies force from, for example, torque or vibration, then the mount actually pushes back with the same force in the opposite direction. Again, same force, opposite direction, but applied to different objects. The crux of this law is that every force you apply is part of an interaction. The object you push pushes back on you. You pull on a rope, it pulls on you. You walk forward by pushing backwards on the ground, and the ground then pushes you forward. Let's now talk about work, which is a way of measuring energy transfer when a force moves something, or when pressure changes volume. Work is denoted by the letter W and has a unit of joules. The formal definition of work is that work is equal to the force multiplied by the displacement. This is a dot product between the force vector and the displacement vector. In simpler terms, it's a measure of how much of the force is applied in the same direction as the motion. We can expand the dot product to W equals the force multiplied by distance multiplied by the cosine of theta, where F is the magnitude of the force, D is the distance moved, and theta is the angle between the force and displacement. This angle matters, as if the force is perfectly aligned with the motion, cos theta equals 1, and all of the force contributes to work. If it's perpendicular, then cos theta equals 0. So in practical terms, work is a measure of effort. How much energy is used to lift something, push something, or compress something? If the force is constant and in the same direction as motion, the formula simplifies to just work equals force times by distance. This is the most common case when pushing or pulling on something across a surface. In chemical engineering thermodynamics, we also care about the pressure work volume. That is the work done when a gas expands or compresses, and is given by the equation here. So to summarize, work is the energy transferred through force and motion. It depends not just on how far you move something, but on how aligned the force is with that motion. It can occur in gaseous, via pressure, or volume changes, not just physical pushes and pulls. Let's apply what we've learned to calculate the work done in a real situation. Here we're pushing a 100-kilogram cart with a force of 700 Newton across a distance of 5 meters. The applied force is 700 newtons. This is the force the person is pushing with. Work is force times by distance. Therefore, work is 700 multiplied by 5, equaling 3,500 joules. This tells us the total mechanical energy the person supplies. This includes overcoming friction and accelerating the cart. In real-world engineering, this is the number we care about when sizing motors or estimating energy use. But what happens to the energy when the object is in motion? It doesn't just vanish. It was transferred into the object. This brings us to the concept of kinetic energy, the energy an object has because it's moving. In fact, the work done on an object is directly related to the kinetic energy it gains. Let's now look at how we calculate this motion energy and how it connects to what we just did. So kinetic energy is defined as the energy an object has because it's moving. We use the symbol Ke for kinetic energy, and its measure is in joules. The formula is kinetic energy is equal to a half times the mass times velocity squared. Let's calculate the kinetic energy the 100-kilogram cart from the previous slide has if it was moving at 4 meters per second. Plugging these into the kinetic energy equation, we determine that the cart has 400 joules of kinetic energy while moving at 4 meters per second. Importantly, the moment the cart has that speed, it has kinetic energy stored in motion. If the cart were to stop, the energy would have to be transferred or dissipated, for example, as heat through friction. What if velocity isn't given and we need to find the kinetic energy another way? Let's build upon the same 100-kilogram cart example we've been using throughout this lecture. So we've already calculated accelerates at 2.5 meters per second squared over a distance of 5 meters, but we're not told the velocity directly. To solve for kinetic energy, we first need to know the velocity. So we use a new kinematic equation here, where the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. Since the cart starts from rest, v0 is 0, and we can simplify this to v squared equals 2 times acceleration times distance. Or rather, the velocity equals the square root of 2 times the acceleration times distance. Plugging in our numbers, we get a final velocity of 5.09 meters per second. Now we can calculate the kinetic energy using the standard equation of kinetic energy equals a half times mass times velocity squared. which gives us a half multiplied by 100 kilogram multiplied by 5.09 squared is equal to 1,295 joules. Let's go back to this work problem. Here we found that the work was calculated to be 3,500 joules, but this was using the force applied. If we had actually calculated work using the net force instead of the applied force, which takes into account the friction force, our work would have actually came to exactly the same value of 1,295 joules. This example shows how not all applied force goes into work. Friction is eating up much of it. Only the net force causes the acceleration and counts towards mechanical work. So when calculating work, always think about what's actually moving the object, how far is it moving, and what forces are opposing this motion. Now let's talk about potential energy, specifically gravitational potential energy, which is where energy an object has is due to its height above the ground. Potential energy is defined as the mass times by gravity times by the height. Let's say an object weighs 100 kilograms and has been lifted to 5 meters off the ground. That means it's storing energy. If it were dropped, that energy would be released as motion. Any object that's elevated, like water in a tank, a raised wave, or even a boulder on a hill, has gravitational potential. It's the energy waiting to be converted into motion. Let's calculate how much potential energy this 100 kilogram object has at 5 meters. So here, the potential energy is equal to 100 kilograms multiplied by gravity, 9.81, multiplied by the height, 5. So this gives us 4,905 joules of stored gravitational energy. Gravitational potential energy increases with both mass and height. Lifting something higher or lifting something heavier stores more energy. Let's see how this potential energy is converted into kinetic energy as the object falls. For understanding this, we now apply one of the most important principles in physics and engineering, the conservation of energy. That is, energy is conserved. It can transform, but it can't be created nor destroyed. That means energy may change form, like from potential to kinetic, but the total energy stays the same. Unless energy is added or lost through non-conservative forces like friction, the full energy balance is initial kinetic energy plus initial potential energy is equal to the final kinetic energy plus the final potential energy plus non-conservative work forces like friction or air resistance. Let's look at this example where a 100 kilogram object is dropped from a height of 5 meters. Let's assume it's stationary to begin with and thus has no initial velocity, and that there's no friction or air resistance as it falls. At the top, the object only has potential energy, which can be turned through the potential energy equation, which, plugging in the mass, gravity, and height, gives us an initial potential energy of 4,905. At the bottom, we assume that the potential energy is zero, as that energy is converted into kinetic energy. The kinetic energy initially will be zero since the object is stationary, but as it is falling to the ground, it will have kinetic energy, which can be determined using the kinetic energy equation. So we get a value of a half multiplied by 100 kilogram multiplied by the velocity squared, or rather 50 multiplied by the velocity squared. Substituting these calculated values into the energy conservation equation, we get that 4,905 is equal to 50 times the velocity squared, which reduces down to velocity equals 9.9 meters per second. So the object hits the ground at about 9.9 meters per second, because all of the gravitational potential energy was converted into kinetic energy during the fall. Earlier, we defined mechanical work as force times displacement, but now we'll extend this idea into systems where pressure is the driving force, like in fluids and gases. First, recall the definition of pressure. Pressure is equal to force divided by area, or rather force is equal to pressure times area. This means a force exerted by pressure over an area can still be plugged into the work formula. Now, if we substitute force equals pressure by area into the work equation, we can get work as pressure multiplied by area multiplied by distance. And since area multiplied by distance is a volume, we can further reduce this to work equals pressure multiplied by the volume of fluid moved. This is the equation for pressure volume work when pressure is constant. But if pressure isn't constant, like in compressible gases or expanding steam, we use an integral to account for how pressure changes with volume. In some cases, if we just want an estimate for a system with an average pressure change, we can use work equals delta P times by delta V, where delta P is the difference between outlet and inlet pressure, and delta V is the volume of fluid moved. Let's look quickly at pressure volume. In this example, a pump moves 0.1 cubic meters of water through a distillation column. We're given the inlet pressure at the column base, which is atmospheric, and the outlet pressure at the column. We can find the pressure difference by subtracting the outlet from the inlet, which comes to 200,000 pascals. The volume of fluid moved is given as delta V equals 0.1 meters cubed. Now, applying the formula for pressure work volume, delta P times delta V is equal to 200,000 times by 0.1, which is 20,000 joules. So the work done by the pump to move the water is 20,000 joules. This is a typical calculation for work in systems like pumps, where pressure changes cause fluid to move and energy is transferred. Now we look at a special type of pump work, when you're lifting fluid vertically, like when you're pumping water up into a cooling tower or storage tank. In these cases, you're not necessarily pushing fluid through pressure. You're working against gravity to raise fluid to a new height. The work done to lift fluid vertically is given by rho, the fluid density, multiplied by gravity, multiplied by the volumetric flow rate, multiplied by the height, multiplied by time, aka the duration of pumping. This equation effectively is equivalent to the delta P delta V equation for work, expressed in terms of measurable flow and height, rather than pressure. This version is often more useful in systems where you don't have a pressure sensor installed, or you care more about the energy required to lift water, rather than the pressure drop. Or you're working in an open tank or cooling towers where pressure is atmospheric, and height is the only thing that matters. It's also common in pump design and energy efficiency analysis for water utilities and cooling systems. Another quick note, flow rate Q is just volume per unit time as shown here at the bottom. So work can be expressed using this equation with time cancelled out. To summarize, use this equation when you know how fast you're pumping, how high you're lifting, and what fluid you're moving. Here's an example using the equation we just saw. A pump is moving water to a cooling tower that is 20 meters high at a flow rate of 0.01 cubic meters per second. We're asked, how much work is done if the pump runs for 10 seconds? We're given the density of water, which is 1,000 kilograms per meter cubed, the gravity, which is 9.81 meters per second cubed, the volumetric flow rate, 0.01 meters cubed per second, the height, 20 meters, and time, 10 seconds. Inserting these into the work equation, we can determine that the pump does 19,620 joules of mechanical work to lift the water in 10 seconds. This value tells us how much energy was transferred by the pump. And if we want, we could now use this to calculate how much electrical power the pump would need. This approach is useful in engineering systems like water treatment, cooling systems, and chemical processes, where flow rates and tank heights are known, but pressure measurements are not readily available. Let's zoom out for a second. Up until now, we've been focused on work. In other words, how much total energy is transferred or used in a system. But in many real-world systems, especially in chemical engineering, how fast that work happens is just as important. That's where power comes in. Power is the rate of work given by the equation power equals work over time, or in symbols, P equals W over T. So if we take 10 seconds to do 2,000 joules of work, the power is 200 watts. Power is also intrinsically associated with efficiency, how effectively a system converts input power into useful output power. Efficiency is defined as the power delivered to the fluid divided by the power input to the pump, multiplied by 100%. Power and efficiency help answer different questions than energy or work. Work tells us how much energy is needed or used, whereas power tells us how quickly can that energy be delivered, and efficiency tells us how much of what we put in is actually useful. This matters because power is what determines how fast we can fill a tank, how quickly a pump can respond, and how large or expensive a motor needs to be. It's critical for sizing equipment, managing safety margins, and designing systems that don't waste energy. Some of these key differences are highlighted in the table below. Let's finish this pump problem by looking at efficiency. We're told the electrical input to the pump is 2.5 kilowatts, 2,500 watts. But how much of that power is actually going into lifting the fluid? Earlier we calculated it takes 19,620 joules of work to lift the water over 10 seconds. So one way we get the power is to take the work and divide it by 10, giving us 1,962. That's the useful output delivered to the fluid, but we could also calculate power directly using an equation on the left, where power is equal to density multiplied by gravity, multiplied by the volumetric flow rate, multiplied by the height. It gives the same result without the need for time, using the same operating conditions. Now let's find efficiency, aka output power divided by the input power multiplied by 100, which is 1,962 divided by 2,500 multiplied by 100, and this gives us 78.5% efficiency. That means about 78.5% of the electrical input power was used to lift the fluid. The rest, around 21.5%, is lost due to friction, noise, or heat in the motor and pump system. This is why we care about efficiency. Even if you only need a small amount of useful work, you may have to size your equipment for much larger input depending on how efficient your system is. Let's now shift gears from linear motion to rotational motion, things that spin, rotate, or turn, like a mixer blade or a centrifuge. This is called angular kinematics, the rotational equivalent of linear motion. Angular displacement, or theta, tells us how much something has rotated. It's like distance an object has traveled, but measured in radians instead of meters. We define angular displacement as the delta theta, which is equal to the final theta minus the initial theta. If object rotates a full circle, theta equals 2 pi radians, which is equal to 6.28 radians. That's equivalent to 1 full revolution. So in revolution, theta is your rotational distance. Now let's look at how fast something is rotating. Angular velocity tells us how quickly the angle is changing, just like linear velocity tells us how quickly positions change. The formula is omega is equal to the delta theta divided by the delta t. Units are radians per second. Let's say a mixer blade rotates at 6.28 radians in 2 seconds. That's 1 full circle. Using this equation, we can determine the angular velocity is 6.28 divided by 2, which is equal to 3.14 radians per second. So the mixer spins at 3.14 radians per second. So in summary, theta is like theta, or angular displacement, is like distance, but in angles. And omega, or angular velocity, is like speed, but for rotation. We use angles in radians because it simplifies the maths and ties directly into circular motion equations. Let's now talk about moment of inertia, symbolized by the letter I. It's the rotational equivalent of mass. It tells us how hard it is to make something spin faster or slower. Here is the general formula, where I is equal to the integral of r squared dm. This means we add up the parts of mass, which are weighted by how far away they are from the axis, r. Importantly, the farther the mass is from the axis, the more it contributes to rotational inertia. Let's look at a practical example, like a solid cylinder, or a drum or a centrifuge spinning around its center of axis. The moment of inertia is defined as I equals 1/2 multiplied by the mass multiplied by the radius squared. This is directly useful for cylindrical equipment like centrifuges, rotating drums, and pump impellers. Now let's compare that to a thin rod rotated about its end, like a mixer shaft or blades on the side. The moment of inertia is given by 1/3 ml squared, where L is the length of the rod. Notice this time how length replaces radius, because it's more about linear extension than circular shape. This rod example applies to mixers and agitators with long shafts and blades. There is also a helpful summary table here shown in the top right of this slide, showing different shapes and how the moments of inertia differ depending on how they spin. You don't need to memorize these, just know the shape on the axis position affects resistance to rotation. So moment of inertia is all about how much mass is involved and how far it is from the axis. That's why a long blade with a wide drum takes more energy to speed up, and why knowing I, the moment of inertia, is critical when calculating angular motion, torque, and energy, which we'll come on to soon. Let's apply what we just learned. We're given that a thin rod, like a mixer blade, is rotating about one end. Thus, we'll use the formula for this shape of I equals a third ml squared. We're told the blade has a mass of 2 kilograms and a length of 0.5 meters. Substituting these into the equation, we get inertia is equal to 1/3 multiplied by 2 multiplied by 0.5 squared, which gives a moment of inertia of 0.67 kilograms meter squared. Even for relatively lightweight and short objects, you can see that length makes a big difference because it's a squared in the equation. Now that we understand how mass resists motion, inertia, let's now look at what resists changes in rotational motion and what causes spinning to speed up or slow down. This brings us to Newton's second law for rotation, where tau is equal to I times by alpha, where tau is the torque, like rotational force, I is the moment of inertia, and alpha is the angular acceleration. Just like how F equals ma describes how linear force causes acceleration, this equation describes how torque causes angular acceleration. It's the rotation version of Newton's second law. So just like with mass, if something has more inertia, you need more torque to get it spinning faster. Torque is what causes things to rotate. We usually deal with net torque, just like net force in linear systems. This net torque might come from multiple things, like motors, as well as negative things, like friction or opposing forces. So if we want to know how fast something's rotation changes, we look at how much total torque is applied, and how much rotational inertia it has. Let's look at how motors apply torque. Motors apply torque through a formula tau equals F multiplied by R, which means that torque depends on the force applied at the radius from the axis. Similar to a wrench, the longer the leverage, the easier it is to twist. In other words, the bigger the R, the more torque for the same force. You can think of torque as the twisting strength, and this equation tells us how much twist we get from a given force. To summarize, making something spin faster requires more torque, especially if it has a high moment of inertia, aka resistance to rotation. Torque depends on both the amount of force and how far from the axis it is applied, like using a longer wrench to get more turning power. Let's walk through a practical example of rotational dynamics, specifically torque, moment of inertia, and angular acceleration for a centrifugal rotor. We're told the motor applies a tangential force of 100 newtons at the edge of the rotor, which has a radius of 0.2 meters. Using the torque equation of tau equals F multiplied by R, we determine torque to be equal to 100 times by 0.2, which comes to 20 newton meters. We're also told the rotor is modeled as a solid cylinder rotating about its central axis. For that geometry, the moment of inertia is determined using I equals 1/2 multiplied by m multiplied by r squared. Plugging in the values for mass, which is 5 kilograms, and radius, which is 0.2 meters, we get inertia as 1/2 multiplied by 5 multiplied by 0.2 is equal to 0.5 kilograms meters squared. This tells us how much resistant to spinning the rotor is. Now we use the rotational version of Newton's second law, where torque is equal to the moment of inertia multiplied by the angular acceleration, or alpha. Solving for alpha, we get 20 divided by 0.5, which comes out as 40 rads per second squared. That's a pretty high angular acceleration, meaning that the rotor will spin up quickly under this torque. We've looked at how things spin and accelerate. Now let's talk about the energy stored in that rotation. What is rotational kinetic energy? Just like moving an object has linear kinetic energy, with half multiplied by mass multiplied by velocity squared, a spinning object stores energy too, called rotational kinetic energy. We calculate rotational kinetic energy using the following equation, where rotational kinetic energy is equal to 1/2 multiplied by the moment of inertia multiplied by angular velocity. Let's now quickly apply this to our centrifuge rotor, which we're told here spins at an angular velocity of 100 rads per second and has a moment of inertia of 0.5 kilograms meters squared. Plug in those numbers into the equation above, we get 1/2 multiplied by 0.5 multiplied by 100 squared, which comes to 2,500 joules. So the rotor stores 2,500 joules of rotational energy. That's energy that can be used to do work or must be dissipated when stopped. This is the rotational version of energy in motion. Just like in straight line motion, faster spin and more mass or distance from the axis means more energy is stored. This is crucial in rotor design and energy recovery systems. Let's now explore angular momentum, which is the rotational counterpart of linear momentum. Angular momentum is represented as L and is defined as the moment of inertia multiplied by the angular velocity or spin rate. Just like linear momentum, which is mass times velocity, angular momentum is rotational inertia multiplied by rotational speed. So what does L, or angular momentum, actually tell us? Well, it tells us how much rotational motion an object carries. That is, an object that is heavier or its mass is farther from its axis of rotation, so larger inertia, and or the faster it spins, the more angular momentum it has. Let's now look at the conservation of angular momentum. If there's no external torque, the angular momentum, L, remains constant, meaning the initial inertia times the initial angular velocity is equal to the final inertia multiplied by the final angular velocity. This means that if I get smaller, like pulling the arms while spinning, then angular velocity has to get bigger to keep the product the same. So just like a figure skater pulling in their arms or legs, the system increases its rotational velocity, not by applying extra force, but simply by bringing mass closer to the axis. This reduces the moment of inertia and causes them to spin faster to conserve angular momentum. Let's imagine a spinning rotor. It starts with some moment of inertia and a spin rate. Now, if the mass moves closer to the center, like arms folding in, then the inertia becomes smaller. To conserve angular momentum, the rotor spins faster, so the angular velocity increases. You may also see this in mixing tanks too. If the material starts to clump or settle, that changes how the mass is distributed, and so inertia changes. If no torque is applied, the mixer may speed up or slow down, all on its own, just to conserve angular momentum. Let's apply the conservation of angular momentum to a spinning chemical mixer. A chemical mixer is rotating to blend fluid and particles. At the beginning, the mass is mostly spread out near the outer edges, giving it an initial moment of inertia of 1 kilogram meter squared. Initial angular velocity is 20 rads per second. As mixing continues, the material settles closer to the center. This changes the distribution of mass and lowers the moment of inertia. The final moment of inertia is calculated to be 0.5 kilograms meter squared. If there's no external torque, then angular momentum stays constant, meaning that the initial moment of inertia multiplied by the initial angular velocity is equal to the final moment of inertia multiplied by the final angular velocity. Substituting in these numbers, we get 1 multiplied by 20 is equal to 0.5 multiplied by the final angular velocity. Solving this, we find that the final angular velocity is 40 rads per second. The key idea here is that the mixer spins faster as the mass moves inward, because angular momentum must stay the same. This is like how a figure skater spins faster when pulling in their arms and legs. Let's now shift to rotational power, which is especially important in systems like centrifuges and mixers. These systems rely on a motor applying torque, a twisting force, to keep them spinning. That torque applied over time produces rotational motion. We already know from earlier that linear power is calculated as force multiplied by velocity. This tells us how much energy is transferred per second when something is pushed in a straight line. Applying the same logic to rotating systems, here we find that rotational power is equal to the torque multiplied by the angular velocity. Here, torque is in Newton meters, angular velocity is in radians per second, and power is in watts, or rather energy per second. This is important as knowing rotational power tells us how much energy per second is being delivered to spin the system. This is critical for selecting the right motor size, making sure your equipment can handle process loads without being underpowered or wasting excess energy. It also helps avoid damage to sensitive systems and ensures efficient operation across different fluid or mechanical loads. Let's now look at the practical example of rotational power and how we can calculate efficiency. Suppose a motor applies 12 Newton meters of torque at 80 radians per second, and it draws 1500 watts of electrical input power. What we want to know is two things. Firstly, how much mechanical or rotational power is being delivered? And then secondly, what is the efficiency of that system? We'll use the rotational power equation, which you've already seen, where power equals torque times angular velocity. This will give us power in watts. Substituting in these values, we can get 12 multiplied by 80, which comes to 960 watts of power. So the motor delivers 960 watts of usable mechanical power to spin the rotor. Now let's find the efficiency. Efficiency is the ratio of output to input power multiplied by 100 to get a percentage. That's 960 divided by 1500 multiplied by 100. This gives us an efficiency of 64%. This means that only 64% of electrical input energy is converted into useful rotational work. The rest is likely lost as heat, friction, or other inefficiencies in the system. Measuring rotational efficiency in chemical engineering is important for minimizing energy waste, sizing motors correctly, and ensuring equipment like mixers and centrifuges run cost efficiently. That brings us to the end of this lecture, where hopefully you can now apply Newton's laws to both linear and rotational motion. Connect force, mass, and acceleration to real motion scenarios. Calculate work and kinetic energy in linear systems. Extend concepts of force and energies to torque and rotation. Compute rotational power and assess pump and motor efficiency, as well as understand how mass and geometry affects the spin rate and energy use.